Yes.
Okay, so we have two terms here. We have the capacity of the section, and then we have the demand. Demand is what you wanted the beam to support. Capacity is going to be how much force or moment or shear, whatever force that you're working with, that this section is going to be able to support. In order for me to do the capacity, which means how much the section is going to be able to support, which means like the strength, if you like to call it also this way, you need to have the section properties. Depth, width, rebars, amount of rebars, location, material properties. And with that, you're going to be determining the strength of the section. And this is exactly what's needed here, the moment capacity. This has nothing to do with the demand. Demand is going to be based on the given loading. Like where, for example, if you'd like to see an example, you're going to be looking at this. You're going to say, here is the demand, something like that. Someone's going to give me here this beam, some loading, and he's going to say dead load and live load. Do you know the difference between dead load and live load? And this is for the person who started the question. Are you still there? Yes or no?
Yes, yes.
Okay. So my question to you, do you know the difference between dead load and live load?
Yes, I do.
Okay. So, and I'm sure that you heard about load combinations, right? Or
Yeah,
no?
yeah, for sure, yeah.
Okay, so load combinations. So for the load combinations, if I give you here, if I say, for example, this is going to be like dead load, and then I said, try to find out the ultimate moment. Is the ultimate moment a demand or a capacity? What's your understanding, Ammar, for this?
The capacity.
Okay, all right. Actually, it's going to be the demand, okay? So it's something that we need to review together. All right, so let me take you here. Were you here last time, Ammar, by any chance?
Yeah.
Okay. The good thing is this, the previous, lecture is recorded, and I would urge you to go back and listen to it. I mean, sometimes, I'm attending like a course or a meeting, and also I'm thinking about something different, and I can just lose track of what's happening. So it's gonna be very good when you take notes, and also when it is recorded. This is gonna be the best. I mean, recorded means go back to it, listen to it a few times. If you didn't get it, ask. So this load combinations, this to determine the demand, which is the ultimate. So this ultimate sub u here, like what you're seeing here, u sub u sub u sub u, means the ultimate. This is a demand, and this is gonna be based on the given information. What given information that I'm talking about? I'm gonna say like dead load and live load, like in here. I'm gonna give you your dead load and live load, and based on this, you figure out the demand, which is this piece of u. So we're gonna say demand is gonna be in this side. Capacity is gonna be on the other side. And as you see here, you'd like to see capacity higher than the demand.
Oh yeah.
Like what? Yeah. So for example, based on given loading, you're gonna be figuring out the demand. Like this John question right in the chat room. Exactly what it means. Based on the given loads, you say like in here, you're gonna be figuring out the demand. How's that? It's gonna be based on the load combinations, dead load and live load and so forth. Capacity here is gonna be based on what? A phi factor, reduction factor, section properties, dimensions, like this case here, right? Material properties. And this is a very detailed example that I give you here. It's how to find out phi man. Now let me go back to this guy, to this example, right? Or to this homework. This is only about the capacity. And all of the steps, effective depth, depth of the compression block, neutral axis, reduction factor, nominal capacity, moment capacity is going to be right here. Nominal capacity, final capacity, total capacity, phi factor. How do you do here the phi factor, right? Here's the beam analysis, depth of neutral axis, right? Strain in the steel is mentioned here. It has not been asked here, but you need this to figure out the phi factor, right? And then all the properties is going to be right here. So This is not going to be adding anything to you. If I give you the solution to it, it's not going to be adding anything to you. It's going to be additionally, it's going to be one more example very similar to this. So what is in here? What do you need from me? I mean, I'm trying to help, right? But I don't want to give you lots of solutions for more than one problem, especially when they are exactly the same. If there's any big differences, definitely I'll give it to you. Let's go here to problem number 1. Has everybody did this? I mean, did you guys done with it?
Yeah.
Safely, correctly?
Yeah.
Any questions on finding out the cracking moment?
Yeah, what was C? It's just half,
What? Say it again. I'm sorry.
like the compression block.
In here, there's no compression block. This is about to study the performance of concrete, about the cracking moment. You remember the cracking moment? Did we study it here? Did we cover it last time?
Yeah.
Is it about this or no? This is when you have reinforcing. The
Yeah,
other
we
one
covered
here,
it
no
before.
reinforcing. And we did this in details. We have studied this, which is this one here. If you remember this cracking moment, you
Yeah.
do FCR, you find out section modulus, and then you find out the cracking moment. This is the cracking moment, right? We went through this. Did we go through this?
Mhm.
I may ask.
Yes.
Just want to be sure that we went through this. So what's the difference between this problem here before cracking and between this problem after cracking? I'm gonna say this one here is gonna be the basic understanding of uncracked section, like homogeneous section, right? And this shows here the performance of the concrete beam before cracking. But this problem here is about the capacity of the beam. This here about the capacity, right? You start to have some rebars. This is why in this problem, there is no reinforcing. No concrete block. We don't have that. This is all before cracking. It says determine the section modulus and then the cracking moment. So all of this is going to be before cracking. And then after given some loads, I'm asking you, have the beam cracked or not? So how do you guys feel about this? Did it crack? Did this beam crack or it is not cracking?
So we check the moment and we see if it's larger or less than. So in this case, it's a crack because the moment is more.
So what was the cracking moment? Do you recall the value that you ended up with?
Sorry, I couldn't hear you.
How much was the cracking moment as in terms of foot?
I believe I got it at 67.88.
Yeah, I think I got it 600 something. And the moment I got it from this question, example number 2, it's 100.
Okay. So which one is higher? You say 600 or 67?
No, 600, I think 78 or something like that.
The demand is going to be higher.
The first question, it will be more than the second question.
Okay, so everybody says they were able to get 67.88. Can you back check your number, please? Quick.
Yeah, that's what we got.
Is it correct?
Yeah,
I'm talking about the 600 case. Is this correct? Is it 600 or 67?
67.
67.8.
67.8.
67.
Okay. So here's from Teresa. Teresa's telling me this is now 6788, right? And this is going to be the cracking moment. So if the beam is reaching 67, it's going to crack, correct? That's my understanding. Now, how much moment did you apply to the beam based on this? It's going to be
More
100.
than capacity.
So
So it will.
the beam is telling you that it's going to crack at 67. Now, you put 100 to it. Don't you think it's going to crack? Now, this is going to be
Yeah.
your demand. This is applied moment to it. And this is how much it's going to be able to take. Let me put this here for quick. Here's the answer to it. I'd rather discuss the answer with you guys instead of posting it. Because posting it means it's going to be in some folder. That's it. It's going to be sitting there. Discussion, we'll understand it together. So based on the first problem here, based on the section properties, right? I was able to find out the cracking moment. It's not really the capacity, but you can consider it to be the capacity at this point. It's gonna be your limited state. It's gonna be the limit after which, or right at which, the beam is gonna start to crack. So we can say, okay, the beam is gonna crack at 67.88. How about the moment? From the moment diagram, when you have this 100 kfoot, moment is gonna be equal to 100 kfoot. Means that the beam is gonna crack. It's that simple. Are we good, Teresa?
Yes, I think,
You-
yeah,
you-
because it makes sense. The moment's
Okay.
bigger than clicking.
Okay, very good. Now, problem number 3 is right here. Look at this. It's gonna be 5 lines, 5 steps, very similar to what we have done here. Right? Exactly the same. Difference is the yield strength is 75 KSI. How about the yield strength here? 60, right? And this problem is gonna be 75. That's it. Everything else is gonna be exactly the same. Look at this. AS times FY, 4. Number 8, 75 KSI. Okay, do we still need to post the solution?
No, I think we got it.
You should be fine, right? Because you have
Yeah.
very good examples in the slide sets. This is what I'm trying to get to add. And I don't want to just add more files to your folders for no need, and something's gonna be sitting there, especially that you have very good detailed solution for these 2 examples in here. Okay. I'm asking you to study the few slide sets that I put from an old course, the 301 that I'm sure that you guys have taken already, right? About the bending, what does it mean by bending? When you have this bending or flexure, at the bottom you're gonna have tension, the top is gonna be compression. This is gonna be very important for you guys to understand it and feel it. What's gonna happen when you apply an axial load, when you apply moment and kind of the deformation, this is gonna be negative moment, and look what's gonna happen. This distance here, which means the top is gonna get compressed, right? It's gonna get shorter. This one here is gonna get longer. So tension is gonna be here, compression is gonna be here. This is what you call here negative moment. This one is gonna be positive moment when you have tension at the bottom, right? Think about the strain and the stress. Same thing that we have done in concrete analysis for the uncracked section, and also for the cracked section. Cracked section is gonna be a point at the capacity point. We consider to be the capacity point, the maximum moment that the beam can take. It's gonna be Phi. It's gonna be very important that you're familiar with this strain relationship, you know, that you go here at any point and then you say, how can I find out the strain? And then you draw 2 similar triangles, for example, and this kind of stuff. It's gonna be very important for you to understand it and feel it, because this is what you're gonna be doing in pre-stress concrete. It's all about that. You're gonna see this a lot. So here's the strain distribution, and here's the stress distribution. This is also uncracked section, like homogeneous. This is for metal. You know that this is originally was made for metal. This type of exercise in the 301, it is made for homogeneous material. Concrete is non-homogeneous because you're gonna see steel and concrete. But before the concrete is gonna crack, that's why we treated this for the uncracked. We treated the concrete to be homogeneous, which means concrete is gonna be able to take tension and compression safely before cracking. Once the concrete, once it's gonna start to crack, performance is gonna be completely different. It's gonna be a different story. So let's look here at the strain distribution. Usually it's gonna be linear relationship. And this is gonna be the neutral axis, right? Neutral axis is gonna be happening somewhere. The section is gonna be perpendicular to this. This is gonna be like the profile of the beam. It's gonna be this profile looking from this side, right? If you look from this side, the beam looks like this irregular shape. To do this irregular shape, usually just explain to you the basics and the concepts. But in our case, it's gonna be either rectangular section, or it could be a T section or an I-beam, because this is what pre-stress is going to be about. Here's the relationship between the strain. Maximum strain is going to be in the top, and the strain at any level, at any point. As you see here, the strain is going to be equal to Y divided by C. Here is Y divided by C. What is C here? Depth of neutral axis, right? Multiplied by the maximum strain on the top, absolute max. Why this negative sign is there in our analysis? Simply because this can be about compression. So they added this negative sign. So you know that this can be negative strain, positive strain. For us, it's going to be up to us, right? We can control this. We can say compression strain and make it positive, tensile strain and also make it positive. But you need to indicate that this is going to be compression and this is going to be in tension. And with that, you should be fine. You don't really need to use a negative sign. If you decide to use negative sign, this is fine, as long as you keep track of your numbers and you know exactly why this is negative, why this is positive. Same thing for homogeneous. I mean, same thing for the strain is going to be the same also for the stress. Here's the stress distribution. In concrete, usually instead of this sigma, use F. So I'm going to say the very standard thing that we use in concrete, that we use F instead of sigma. This is going to be for the stress, right? Maximum stress is going to happen also in the same point. I mean, if the maximum strain is going to happen here because neutral axis is shifted down, so the strain here is going to be harder than the strain there. Same thing for the stress. Maximum stress is going to be happening on the top. Now, but someone's going to say, you can't really compare compression to tension. So if you like to say maximum compressive stress is going to be right here. Maximum tensile stress is going to be this value. So you can do this. So you can have two maximums. Why? Because one of them is going to be the negative value, negative stress is going to be compression. The other one is going to be the tensile stress. It can be positive. So you have here two extremes, right? The stress at any level at point Y measured from the neutral axis is going to be also given by the same equation. And this is a beautiful thing about having homogeneous section. So everything, I mean, there is no cracking. If you like to consider the concrete to be homogeneous, this is going to be just all the way between the zero stress all the way to the cracking point. So as you see here, we can utilize exactly the same equation. Again, usually C is going to be depth of the neutral axis, measured from the compression. It's going to be C lowercase. If you like to do this integration, you see this integration for the stress, which means finding out the volume. It's going to give you the compression force. So this dF, in our case, in concrete, we call it C. It's going to be the compression force. It's going to be C uppercase, not C lowercase, because it's going to be C lowercase, right? And C is going to be equal to that volume, which means integration. It's going to give you here the force. Same thing for the tension. You're going to have another force here, which is going to be the tension. It's going to be coming this way. Same thing with integration, if you like. Now, the stress distribution also is given by this equation that we have used. We have used this already. It's going to be the moment divided by I, M divided by I, right? Moment of inertia multiplied by C. What is C? The depth of the compression, the depth of the neutral axis, the distance from here to there. So if you're interested in the stress at any level, like if I take you back here, the stress at any level, like this is stress value, this sigma is going to be equal to the moment divided by the moment of inertia times Y. For the maximum stress value, you say it's going to be times C. And this is the reason that we have Y top and Y bottom. Someone's going to say, what Y top and what's Y bottom? I'm going to say, you know what? Let's just go here to this review that we have done last time. Let me go here to Y top and Y bottom. Maybe right here. You see this Y top? This is going to be Y top and Y bottom. What is Y top? The distance from the neutral axis to the top, all the way from here to there. If I may add an arrow, it's going to be this distance, say from here to here. We call this going to be Y top. What is Y bottom? The distance from the bottom all the way to the neutral axis, this distance here. What do you call this? It's going to be Y bottom. It's going to be very important that we know exactly which distance we're going to be using. Interested in the stress on the top, what would you do? You use this, right, in your equation. M divided by I times this Y top. And there isn't the stress at the bottom. You take the moment divided by I multiplied by this Y bottom. As you see here, in my analysis, I didn't put negative and positive, right? I didn't do that. Because in concrete design and concrete analysis, we don't do that. We just keep all the values positive, and then we say compression, then we say tension at the end of the analysis. In the past, when you have taken the 3-1, the uses call this going to be negative and this is going to be positive. And this is going to be exactly the same equation, right? Exactly the same equation. If I may look here, exactly the same equation. M times Y divided by I, which is exactly this equation here. M times I divided by Y. Okay. Here's a homogeneous section. As you see here, it's made out of wood. And then based on this, we were able to find out the moment of inertia for this given section. And the stress can be determined using this equation here. If you look here, here's the moment. Your moment is equal to this much, right? And then multiplied by C. What is C? Let's give you the 6-inch. Divided by moment of inertia, which you just calculated out. One steel beam and some analysis to find out the stress and the stress distribution throughout the depth of the beam. It's going to be very important stuff for us, and we really need to understand it. You know, you really need this. Let's say now combined loading. This is the way it was named in the 301. What is this combined loading? In the combined loading, you're going to have normal stress in the section due to axial load and due to moment. In the previous slide said, it was also about the applied moment. You just have some moment and that's it. Like simply supported beam, you apply some moment and then you get some flexural stresses. It's going to be normal stresses. Top is going to be compression, bottom is going to be tension when you have positive moment. But here's one case. Once you apply here some tension, what's happening? Now in this case, you apply here compression and also apply some moment, and the moment is going to be equal to this force multiplied the distance from this, you can see the blade, right, all the way to the top of this arch, if you like. So here's what we have. We have combination of axial force and flexion. So it's going to be axial force applied. How do you find out the stress? The stress is going to be equal to the axial force P divided by the cross-section area. It says here P divided by A sub 0, original, before it start to shrink. So you can see this is going to be like the normal force. Due to what? Due to axial load. So all the stress that you are working with, you can call it normal stress, because it's going to be perpendicular to the section of interest. This is going to be our section of interest, right? Just because of the axial load, it's going to be P divided by A. And due to the flexure of the moment, it's going to be M divided by I times C. Okay, great. Now I need to combine it because in my section, I'm going to have moment and axial load in the same time. So here's the case. Here's one section, right? I'm going to apply here this P divided by this cross-section area. This is like an elevation of it, right? You can see here the stress at point 1 and 2. This can be the same. We'll call this sigma P. The stress due to the axial load. I call it sigma sub P. Just to make it to differentiate between this and between the stress due to the applied moment. Stress at 1, the stress at 2 is going to be exactly the same. It's going to be uniform because you just have an axial load. You take this axial load divided by the contact area, you get the stress. It's going to be the same throughout the entire area. If someone here says, if I give you the stress here, can you find out this applied load P? I'm going to say yes. Just do the integration. Take this stress, multiply by A. It's going to get you the volume of this stress block. It's going to be sigma P times A. You get the P, the axial load. It works, yes. How about when you have moment? I'm going to say when you have moment, I'm going to be labeling the same points, right? This is going to be point 1, the left side, the right side, left side, right side, 1 and 2. The stress due to here, the moment is going to be equal to what? It's going to be equal to the moment, applied moment, bending moment, divided by the moment of inertia times C. Now, what is C? I'm going to say C is going to be the distance from here to there. It's going to be C. C lowercase, not uppercase. Depth of neutral axis, which is the same as the C here if you have symmetrical section. Now, in this side, according to what I'm looking at, this here compression. So compression is going to be going up, right? So this side is going to be compression, and this side is going to be tension. And here's the stress equation. So I was going to say, if I'm given here this is stress distribution, can I do integration, find out the moment? I'm going to say yes. Very similar to what we have done in the strength, in the force, or the couple method, right? I'm going to come here and do integration for this prism, for this triangular distribution block. The same thing here. I'm going to have here tension, compression, multiply this by the moment R, this between the two, you get you the moment. Now, when you do summation of the force in this direction, you're going to see that this tension is going to be the same as this compression force. They're equal to each other. Therefore, there is no force in this direction. And this makes sense because this is only moment. Now, I'd like to combine the two stresses. I have a stress due to axial load and the stress due to moment. So let me go here to the first point and see how much is the stress due to axial load. Stress due to axial load is going to be called sigma P. Here's P over A. Stress due to moment is going to be tension. It's going to be M divided by I times C. And this is why it says here sigma 1, 2 for these 2 points. It's going to be P over A compression plus or minus M over I times C, which means it's going to be the stress. Now, this is the way that we do it in concrete design, right? We do the stress as an F. We don't do it sigma anymore, right? So we're going to say F due to P, the axial load, plus or minus F due to N. So in one side it's going to be additive, and the other side is going to be subtractive. Now, which side is going to be additive? Is it side 1 or side 2?
Side 1,
Side 1. How's that?
because it's in tension.
Side 1 is in tension, right? How about side 1 here? Is this tension? Look at the direction of the stress. Look at the direction of the stress.
Oh, no, it's in
So
compression.
side 2 is compression, right?
Yeah.
Side 1 is tension. Here, side 1 and 2 is going to be in compression.
Oh, okay.
So someone here is going to say, I'm a bit confused because we keep on using this. You know, in the past, we keep on saying that tension is going to be positive, compression is going to be negative. So now I want you to just put this aside for now and just think about, is this tension or compression? Because it is very good idea, of course, when you keep track for the positive and negative sign, right? But in the same time, you need to keep an eye on whether this is really tension or compression. Do you have a feeling for it? The physical, I mean physically, is it like tension or compression? This can be the physical meaning of the positive and negative sign. If you don't keep track with this, you can do a mistake easily. But later on, once we start to do our pre-stress analysis on given sections, we really need to keep track of the sign. And from time to time, we're going to go into the equation and look and see if this is going to be tension. And then we say, yeah, tension is going to be positive. This makes sense. Compression is negative. Is this really tension or no? Or did we do a mistake in our formulation? So this side here, I'm going to say is going to be subtractive, and side 2 is going to be additive because it's going to be compression. This is also compression. One example, they give you here a force on the column. So here's one concrete member. If you like to call it concrete or maybe wood or metal, it doesn't matter. And then we start here to put a point load. It is very important that you understand this point load. It can be also a pre-stress force, just, you know. So I want here to start to connect between this and between pre-stress. But someone's going to say, I don't know what this is about. I understand. We don't know yet. But you know what? Just think about this 150 pounds as just to be a point load at a distance of 5 inches, right? You can say from where? From this neutral axis. Say fine. So this section here is exposed to compression force and also moment. So usually what happens, I can convert this force into force here right in the centroid and a moment. And the moment is going to be coming like this. And putting compression, the arrow is going to be coming down this way. So this 150 is equivalent to a moment and an axial load. So I said, okay, make it equivalent. I'm going to be taking here just to put at the bottom, which means this is going to be equivalent to this. As if you can put here this point load from the top, 350 plus 750 pound-inch as a moment coming this way. Why 750? Just take 150 multiplied by 5. It's going to get you how much? 750, right? Okay. And then after that, we do the stress due to only axial load. And then we do the stress due to what? Due to moment. And which one's larger in value? Just say this one's larger in value. Now I'm looking at the equation here. I'm going to say, where's this negative and positive thing that you're talking about? I don't see it, right? I don't see negative and positive because they just put the pure value, just the value itself, scalar value of the stress. And then they're going to say, well, this can be usually compression, and this one, it can be once tension and once compression. So total compression is going to be the addition of this two. So it's going to be 15. But when it comes to tension, it's going to be 11.25, subtracting the 3.75. Exactly what we have here. And look at the end, they start to put the signs, just to keep track of the signs and be sure. It's going to be tension. It's going to be a very good practice when you say it's going to be tension. Yeah, it's positive. And the compression, as we said, is going to be negative 15 by just adding the two values. It's going to be compression, it's going to be negative, right? And for the tension, it's going to be the difference between the two. You see the tension here, they put it as positive value, and this is going to be compression anyways, right? So it's going to be subtractive, you end up with a little bit of tension. Any questions? Yes? Questions? No? All right.
I think we're good.
Excellent. Another example, point load, some eccentricity. We call this eccentricity. This is why it says E. E stands for eccentricity. So we have two things. We have concentric and eccentric. We have two terms here that we usually use, concentric and eccentric. Someone can help me with the difference between the two? This is the centroid point. Yes? Can someone help? What's concentric? Is this a concentric case or eccentric case?
Eccentric.
Eccentric loading. How about concentric loading is going to happen when I have the point load right here, right at the center. We call this, in this case, concentric, and this one we call it eccentric loading. Okay? Yes, absolutely. Thank you, John. All right, so we did here some analysis, and based on this analysis, because this problem is kind of tricky because they say what's going to happen when the stress is going to be equal to 0, when there's no tension, and then they talk about the core. If you guys recall this issue, there is certain like box or certain area within which if you just put the point load here in the middle, you're not going to have any tension on any of the sides. And this is going to be like an exercise to figure out this area, if you like, or this scope. Another problem here, you're going to have compression. And also you're going to have some moment, and the moment is going to be equals to P multiplied by the distance from here all the way to the center of the section. So this problem here is like a column and then 2 point loads. Both of them are eccentric loads. And you have eccentricity in both directions. What do I mean by that? You have eccentricity in the, if this is going to be the Y direction, this is going to be eccentricity in the Y. And then you have also some eccentricity in the X direction. Look at this. So actually you're going to have My and Mx. Usually My is going to be the moment about the Y-axis, moment acting this way. Mx is going to be the moment about the X-axis, going to be acting this way. Putting here compression. So in a case like this, the equation is going to be a little bit complicated. We're not going to be doing, we call this biaxial. You know, when you have Ex and Ey, we call this biaxial loading, but we're not going to be doing it. Usually, we're going to have just uniaxial when it comes to moment and stress distribution. Questions? We're good? All right. We have some concepts and some basic stuff that we need to discuss here when it comes to the 463. This is about precast and pre-stress, some stuff that you need to know about. This is like a little bit of history about the pre-stressing and how it was developed and evolved. and it starts some time ago. And if you see here, it starts 1824. But some people would say no, the pre-stress idea or concept start earlier, much earlier. I'm gonna be running a small video for you, a short video, but before we do this, I'm just gonna come here and just show you one example that I personally have seen. There is a kind of a museum, if you like to call it this way, out there in Rancho Palos Verdes, and you're gonna see this pipe. This is actually an actual piece of pipe. This is like a water pipe made out of wood. And what do? They bring this cable or this wire, and then they apply the tension to it. So they really do it very tight. And this is actually pre-stress. Because the stress that you apply here, it is true it's gonna be like tension in this wire, in the spiral, but it's gonna be also compression on the wood section itself. So this wood section is like a pipe composed of two pieces, right? It's like two pieces of wood like this. And then once you start to apply the wire around it, right? And then you start to pull the wire. When you pull the wire, you put tension on the wire itself. And of course, one side's gonna get anchored. So here you're gonna come and anchor the wire to the pipe itself, and then you're gonna start to run it around it. And then at the end, you're gonna apply some tension. And during this process, you're gonna apply lots of tension on the wire itself. Now the tension is gonna be in the wire, but this pipe, the body itself of the pipe is gonna be exposed to high compressive stresses. This is why we call here pre-stress. So actually this pre-stress is nothing new. This has been there forever. And here's another section of the pipe. Look at the pipe composed of few pieces. This is for gonna be for larger pipe. And look also for barrels. I'm sure that you guys have seen this is nothing new. This is very old. So it's not really 1824, it's even before this. So what does he do here? In order for them to form the barrel in this case or in this shape, you do it out of wood pieces, and then they start to put this steel strap, and then they start to apply tension. So once they put it, it's like a belt, you know. And once they put it, they're gonna start to put some tension on the strap itself. Once they do this, actually they're applying compression on the barrel body. But what they are doing to the strap, they're applying tension to it. Because look, it's gonna be like the belt, right? You apply the tension on the belt or the strap, and the strap itself is gonna be doing compression. Just imagine, think about every day when you put on a belt, right? What do? You apply tension. Now this tension is gonna be in the belt itself, but on your body is gonna be compression. So this is why we call it here pre-stress. So here's what you do. You apply tension, right? And this tension is gonna be causing compression on the body itself, the body of the barrel. Is this helpful? This compression? I'm gonna say yes. Because what's gonna happen, you're gonna fill this barrel with some fluids. And the fluid is gonna be pushing the body of this barrel to outside. So what you have done, you have started to put compression before you start to put the loads. And the load here is gonna be the demand that you put in there. So your demand wants to open this barrel, wants to open this ring out. And what you have done, you have put already some tension on the ring, which means compression on the tank itself. So before you start to apply the load, you start to apply this pre-stress, which is completely different performance and concept from the conventional reinforced concrete. In reinforced concrete, you put the rebar in the concrete, and then you just leave it there. No loading, no moment, nothing. Everything is good, no stresses, right? Think about it this way. If I bring here a concrete beam, I'm gonna put it like this. Put on the floor, completely on the floor. I'm not gonna say that this beam here is gonna be supported by a couple of columns, and this is why if this is gonna be your beam here, under its self-weight is gonna be sagging down and you're gonna be develop some stresses. I'm not saying that. All what I'm saying, just take the concrete beam and put it on the floor. No loads, no deflection, no strains, no stresses. So the beam is not stressed, it's not used yet. Pre-stress is different. Same thing. Let's say that I'm gonna bring here a barrel like this, a container, right? I'm gonna bring a container, plastic container. I'm gonna just put this plastic container here. It's gonna be filled with air, and outside you have air. Is it stressed now? Can you say that you develop any stresses or any strains in the body of the barrel itself or this container? You're gonna say no, because there is nothing inside. And if you have air inside and outside, they balance each other out, and we don't have any stresses, we don't have any strains. Make sense? In a plastic container, this is going to be the case. Are you guys there?
Yeah, it makes sense.
Okay. Now look at this barrel here. This is different because before I start to fill it with fluid, with water or whatever, right? I applied already some stresses on it. So now it's exposed to compressive stresses, even before I start to fill it with fluid. So if you just bring this container or this tank or whatever, or this barrel, and put it there on the ground, it's going to be exposed to some stresses. Now the stress is going to be coming from the applied force that you put and the stresses that you put because of this pre-stressing. So now pre-stress beams, you start to see stresses before even you start to take them to the side, before you start to use them. They have some internal stresses. It's kind of tricky.
So, Professor, I have a question.
Yes.
So we don't have any compression here before we pour the liquid, or we still have the compression here?
Before even you put it with fluid or any liquid or anything in there, right?
Yes.
You have lots of stresses coming from the pre-stress.
Right.
Because, okay, think about it this way. You're going to put on your belt, right?
Right.
And you're going to put it loose.
Right.
Any pressure on your body?
Yes.
No. You're going to put the belt loose.
Oh, yeah. Yeah. No pressure. No pressure.
No pressure at all, right? This is going to be like conventional concrete.
Right.
Now start to put tension on the belt. Let it squeeze your tummy, right? Your belly. So what's going to happen? Now you start to put pressure on it. This is like the pre-stress. Now the belt itself is going to see tension and your body is going to see compression.
Oh, now that makes sense.
Now, before even you start to drink, let's say, water and get full, to put some pressure on the belt, now you already have some pressure on the belt, right?
Right.
And the belt is putting pressure on your body. This is like the pre-stress versus the conventional concrete.
Makes sense.
So in conventional concrete, it's going to be very similar to someone who's going to put the belt, is going to put it loose, and is going to drink and eat. So what's going to happen? Now his body is getting larger, his abdomen is getting larger. Now he put pressure on the belt. Now he starts to use it. Now we have some stresses and strains in the belt. In the pre-stress, you start by putting pressure first, even before you start. So what's going to happen? Your body's going to feel it.
Right.
Because you put pressure on there even before you eat. You're not going to wait for the load to come and then you start to resist it. This is happening in concrete design. So in concrete design, the tension is not going to be triggered in the rebars unless the section is going to start to crack.
Right.
In our case here in pre-stressed, the beam is already stressed before even you start to put it to use. You have lots of pressure in there. I mean, this is the way it works.
Makes sense. Thank you.
No problem. Important features in like key bridges that maybe you'd like to know about it, which is this walnut, the Lay Memorial Bridge, very important. That received some award and is a good picture that you know. And I'm sure that now you see lots of bridges like this, but you're talking about 1978, right? So 1978, that was like, wow, right? But now it's not really, because you have lots of other pre-stressed bridges. So in pre-stress, what is pre-stressed here? What is made out of pre-stressed concrete? It's going to be this beam here. And this beam also is precast. So you don't cast it here in place. You don't do the form work. What they do this, they go to a yard, they pour the concrete, and then they put the tension on the strands. The strands is going to be like the rebars, or you can call it tendons. So you have a few names for it. Strands, tendons, cables, pre-stressing rebars also. All of that, you can put tension to it. And then they ship it. They put it on a big truck. I'm sure that you may have seen it already. And then they start to install it. So it looks like steel construction, but actually it's going to be made out of concrete. It's a different product, right? You just put it in place. So you don't really need to close this roadway for a month because you want to pour the concrete. This is going to be closed for only maybe 2-3 days, maybe the same day they can be done with it, right? And just once you put this in there, Now they can go on the top and then start to form for the deck. So the formwork itself is going to be supported by these beams. So it's going to be saving lots of time and hours, right? This is what you call here hollow core deck. I don't know if you guys have seen it, usually used in parking structures. The good thing about it is it's going to be much lighter than just solid concrete. And it includes lots of very small wires, like for pre-stressing. And as you see here, you carry it and then you put it. It's going to be very similar to steel construction. It's going to be all precast, pre-stressed. So the depth of it is going to be much smaller than that if you have done it out of conventional concrete. You just carry it and put it there in place. As you see here, this is also precast column, precast beam, and then you have precast blanks, or you can call this hollow core deck. You can also have all of this is made out of concrete, right? Look at this, precast concrete walls. The entire building can be made out of precast if you like to. And you just have a big crane and it's going to be carrying the pieces and just put it in place and assemble it. The real bad thing about this type of construction is going to be the connection. The connection needs really to be of high quality. I mean, you cannot just do any connection, especially when this building is exposed to earthquake forces. Because when it comes to bearing, this is going to be easy for you because you can put like, you know, this small cantilever, right? Which is a corbel, we call it corbel. You can make it strong and can be also precast. But when it comes to this connection for the load in this direction, it's going to be really tough to make it work. So this is going to be kind of tricky in your analysis. Look at what happened here. Here's a column. Comes with some corbels right and left. And then they put, this is going to be like inverted T. You see this? It's going to be inverted T. And then they bring this beam and then they put it between columns, as you see here. And on the other side, this is not a beam, they call this a spandrel. So this is like a spandrel and also a beam. So it's something like this, but it has like a guardrail, you know, for the cars, because you don't want to hit this and just fall with your car, right? So you need to have some protection. They do this spandrel out of concrete, and then they install it to the concrete column. And then after that, they bring this is what you call here double T. So here's the double T. So each one of these strips with a concrete slab, it comes at one piece, and we call this double T. Same thing, they carry it, they put it in place. It is very famous, this type of construction, very famous when it comes to parking structures. So someone's gonna say, how about structural steel? Why don't we do it out of structural steel? Because the structural steel is gonna be very noisy. And the deck performance is not gonna be as good as this. You know, in structural steel, you're gonna have steel columns, steel beams, and then you're gonna have metal deck, and then you're gonna have concrete topping. The problems that you're going to be facing in structural steel, park construction is going to be a lot compared to that. In some buildings, when you have a structural steel building, and let's say the structural steel building is going to be going up maybe 5-6 stories, so you don't really want to do it out of precast concrete. And then you have subterranean parking structure, like 3 or 4 levels. I have designed one of these buildings, and we really have to complete the whole thing out of structural steel. So the 3 parking levels were made out of structural steel. Concrete deck, we made it 4.5-inch hard rock concrete. I mean, it should perform well. The problem was the noise, because you have the ramp and people start to speed up while they're going down, and you see lots of sounds, and they couldn't stop it. I mean, they tried their best. They say, what can we do? And they said, okay, this is what you get when you do structural steel parking structure. And this is one of the problems. Other thing was also the rust, because in parking structures, users can be open to the rainfall, and this can be creating some problem with the steel. It needs more maintenance, and here is going to be less maintenance, because you can design your concrete here not to crack if you want to. This is a famous building, and if you look here, concrete columns, it comes as 5-story column usually. This kind of an optimum design is to have 5-story column. And then you're going to have spandrels, you're going to have inverted T-beams, and then after that you can put blanks, or you can put hollow core deck, or you can put double T's. Here's a double T. This is what I was talking about. You have two stems or two webs, if you like, and then concrete slab. You just carry it and put it in place. It's very fast. Look at this. What happened here? Why here you're using here double T and here you're using core slab? Can someone guess? Yes? Why this is double T and why this is Gabi hollow core? And
Well,
which
I
one do you
think-
think is cheaper?
I think we're gonna have more tension on the first floor, isn't it?
Which one has larger span, the double T or the core?
Double T.
Double T. And which one is deeper, the double T or the core? Is this
Core.
deeper or this is deeper?
I think double T is deeper.
Double T is deeper. So what range are we talking about for the double T? Can I tell you this? Start at 20 inch, 22 inch, 24, 26, 28 inch. This can be the range. So this depth here, let's say about 2 feet. How about this guy here? I'm gonna say maybe 8 inches. There's some 6 inches. There's 8. There's 10 inches. So this is good here for short spans. It's gonna be good. It's gonna be economic. But once you go to larger span, you really need to have this double T. What spans are we talking about for double T's? What is the maximum span that usually, or the optimum span? You say maybe about 50 feet. So this can span here about 50 feet, no supports. Just gonna be one piece. And this width can be maybe 8 feet to 10 feet. So just imagine how fast you can cover this area here after you put the beams. It goes very fast, right? Very interesting. All right, here's the double T. This is the way that they carry it. And then sometimes the double T itself, it comes with a notch. You see this notch? Because the beam is gonna come and this gonna be sitting within the beam, right? Look at this, right? And they carry it from the top. So you have this hooks, it comes with it. When they put it in the planet, from the factory, just comes like this. They carry it with a crane and just put it in place. So you have two types here of double T's. Look at the difference between the two. This double T, they come here and then they notch it. So the support of this double T to the beam is gonna be throughout this piece here, right? This beam or this double T is completely different. Where's the notch? You don't see a notch. And the support is gonna be happening here at the bottom. In some cases, the support is right here on the top. They put a connector there and just support it with it, you know? So there's different, I'm gonna say, type of detailing, and it just depends on the manufacturer, the precaster. Each precaster would like to go a certain way. There's nothing like better than the other. It is their preference. And of course, when you speak to each one of these precasters, every one of them is gonna tell you the reason that we use this because the problem that you're gonna see in this connector. And the other one's gonna say, no, we have a problem with this, right? Because usually this piece can get damaged easily during transportation, and we don't want to take a chance. The other people would say, we don't like, it's called here Ghazali hanger, right? It's like the connection on the top. They say, we don't like this hanger because it may rust later on. After 20 years, you may see some rust in there, and then it needs to be repaired. So we don't want to see this. I say, okay. This is a very famous building. And I personally work in this building, San Francisco, intersection of 3rd and Mission Street. The tallest reinforced concrete building in the West Coast, 39-story. That was designed 2003, 2004. The entire building is made out of reinforced concrete, pre-stressed. All of this level, they are all PT slabs. And also the lateral system, all the columns. Lateral system means like the size of a frame. It was made out of reinforced concrete, pre-stressed. It's a system called like Duodec. I don't know if you guys hear about it. It's a German company, very famous in pre-stressing. It's called Duodec. And they have this system that you call hybrid system. to include some cable and things like this. It was a very interesting project. Design started 2000, and the building was completed, I guess, 2004. We spent lots of hours just on the slab design. I mean, that was kind of a hassle for us. We're gonna take a break here. Let's make it like 10 minutes. We'll be back 8:15. All right? Are you guys there?
All right.
Right.
Yes.
All right.
Great.
Thank you.
Sounds
Very
good.
Right, 8:15. Just within this slide set, you're gonna see all the links. So this link is right there. If you like to watch it again, it's gonna be right here. Truth's here. So that was the one that we just watched, right? Here is the floor plan of the building. The core, yeah, 4 stairs, 4 elevators. In some locations, you have a 5th one. So you have 5 total elevators. And actually, that was a moon frame system. So moon frames were just surrounding the entire structure. You have a moon frame here, another one here. So this arrows here is going to be for the moon frames. And the slab itself was made out of 8-inch PT slabs. Here's a common pre-stressed members, if you like. Here's a double T. It's kind of standard information for it. And as I said, it goes from 22-inch, maybe 24, 26 inches. And the width sometimes going to be 8 feet, sometimes going to be 10 feet. And in some cases, can go all the way up to 12 feet, I guess. So if you look here at the pre-stressed member, the pre-stressed precast member is going to be this one, the light one. The shaded one is like concrete topping. You pour this on the side. So after they install the double T, they're going to come back and put 2 to 3 inch of concrete. Most likely, it's going to be normal weight concrete. And this is going to be our diaphragm for the seismic. So the diaphragm itself is going to be very thin. As you see here, it's going to be made out of maybe 2 to 3 inch of concrete. And very similar to the structure steel. You don't really need to calculate the weight of this double T because you're going to have it in the tables. We have tables of properties for double T's. And also the moment of inertia, you don't really need to calculate that. As you see here, sometimes it's going to be complicated. So they give you the moment of inertia for this section here, for each section. So you go there to the section, you pick the depth, you pick the width, and here we go, you're going to have the moment of inertia, neutral axis location, which means they're going to give you like this. They're going to say, here's the neutral axis, right? Where exactly it happens. Y top and Y bottom. You're going to have all of these variables. So this can be easy. You don't really need to spend any time on it. It's going to be given to you. In the PCI document that I'm sure that maybe lots of you guys, you downloaded the latest version. Am I correct about this statement? That you guys downloaded it? Yes or no? Yeah? Are you guys there?
Yeah, we're here.
Yeah.
Yeah, you download it. So you're going to see lots of tables about this double T, about the solid flat slab. And as you see here, that this going to be like the solid slab is going to be very thin, and also this going to be like the concrete topping that you put on the top of it after you install the slab. This works here for a very short span. It doesn't go that much. And as you see here, this is going to be all the cables that they usually put in there. The cables in this case for the double T is going to be usually at the bottom, the web, right here. But here is going to be distributed. This is going to be also the hollow core. The concrete strength usually is going to be 5,000. They don't go below 5,000 when it comes to concrete. But when it comes to the ultimate strength for the pre-stressed itself is going to be 270 KSI. Now compare this with the standard 60 KSI rebars that you have. So as you see here, the cable themselves, they have high strengths. They are high strength cables. They go to 270, and again compare this to 60. How many times you're talking about? 4 times stronger? So the material here is superior, stronger material that you're going to be looking at and use. And here is the hollow core slab. Now for this hollow core slab, this is 4 inch. Now we're able to make it 12 inch. And actually this is going to be lighter. Why? Because you're gonna put, this is gonna be like holes, right? It's gonna be very open. So it's gonna be much lighter. And here the cable distribution. Here are the cables. When it comes to beams, sometimes we have this rectangular beams. And in this case, if you have a double T or another thing, is gonna come and sit on it like this. And the other double T is gonna come from the other side and sit like this. So it's gonna be totally supported. In some other cases, the double T is gonna come and sit like this. Like this. It's gonna be like this here, right? And from the other side, it's gonna come like this. So this is gonna be like inverted T, and then it's gonna have a ledge. So which part that we call the ledge? The ledge is gonna be this part here. This piece that sticks out, right? So this beam is gonna have two ledges. You just bring the double T and you put it right here. According to the other picture that we were looking at, also the double T can be like this, if you like. Let me use this tool. It's gonna be like this. It has a notch, right? It can be something like this. Here's a double T. Then you have another one coming from the other side. So it depends on the precaster. Each precaster again have their own, details that they'd like to use. Same thing here. This is gonna be like when you have only a double T from one side. So you can have maybe something like this if you want to, or you can have it with a ledge. You can use this as a ledge, and you can do notch. If you like, this is gonna be notched like double T. So it depends on the use. And as it says here, this concrete is gonna be 5,000 FPU, is gonna be 270 KSI. It's gonna be half-inch diameter, and this is gonna be the type of the strain. This is all is gonna be called pre-stress, and it's gonna be pre-tension. Now I'm not clear about now the word pre-tension and post-tension. So what does it mean by that? Now we have pre-stress. Pre-stress means that the member itself is going to be stressed before you put it to use. We understand this. And the pre-stress itself, for the technology, it can be post-tension or pre-tension. So what is post-tension? What is pre-tension? Post-tension means that the tension is going to happen after the concrete is hardened. So when the concrete becomes solid, they start to put the tension on it. They do the pre-stressing. The pre-tension, they put the tension on the cables before they pour the concrete. Does it make sense or no? Not really.
Yes.
Yes.
I mean, I'm trying to picture it, but I can't picture
Yeah,
it.
we'll picture it right now. We're gonna have a few videos here. So here's the method of pre-stressing. And of course, as it says here, you see we have more members that we can talk about, like we have piles and we have columns. It's gonna be all pre-stressed. This is fine. Here's the pre-tension method, one of the pre-tension methods. So what do? You put this in the abutment, like it's gonna be like you have this solid concrete slab. They say like slab and grade in the yard. And then of course they put some plastic or visqueen. Sometimes this is like metal, they put a metal base, like a bed. They call this a bed. And then they come here, they put some abutments, like strong sides, and it's gonna be anchored to the floor. And then they put the cable for the tendon, and then they put the tension to it. Now, do we have concrete yet? You see, no, concrete is not there yet. And then they apply the tension. Now, where's the tension going to? What is taking this tension? What's supporting it? What's keeping it in place? Is it the concrete or the abutment? So it's going to be the abutment, right? All the force here is going to the abutment. Because once you start, let's say that you're going to put a jack, an anchor from here, right? This is going to be a cable, it's going to be coming with this piece, like an anchor piece. The cable is going to be this way. You're going to start to apply here tension, right? You apply tension by jacking it, right? You pull the cable. And then at certain point, you're going to put the anchor down. Now take the jack out and you put the anchor. So it's going to happen after this. Now, this force is actually as if you have put a force on the abutment like this. Now forget about this tension force. You don't now have any tension. Tension force is going to be within the cable itself, within the tendon. Now we're going to have 2-point loads coming like this, and each one of them is trying to break this abutment. They're trying to bend it this way. Now the abutment needs to be strong enough. It cannot deflect, it cannot deform, because once it's going to start to deform, the tension in the cable is going to be gone, right? And then after that, you pour the concrete. In 6 hours, the concrete is going to harden. Next day, the concrete now becomes very solid, and there is now full bond between the concrete and between the tendon. In a few days, now the concrete is 100% hardened, and there's full bond between the cable and between the concrete. Now you can take this out, because the force now has been transferred to the concrete once you cut this down. Now we're going to come from outside, and then we're going to be cutting this anchor with a grinder. You can just cut it from both sides. Once you cut it, you can take this abutment out. And what do you do after this? Now you have your system, right? You have the beam, and then you have all the tension is giving the cable, and all the compression is going to get transferred to the beam itself. Any questions?
So would you need any reinforcement besides the tendon? Or
Yeah, you may need, yeah, if you like, you can put of course. I'm gonna run here this video for you. Hope that you like it. Give me a second. Shows you the process, which is very interesting. Company called Spankry, very famous precaster. They do lots of work, like parking structures. Cool. The hollow core. You can trim it. And this is the concrete topping. You hear me? This is the concrete topping that you're talking about. After you put it, you're going to pour the concrete, which is going to work as a blank. Another one coming through the tube.
tie our lanyards off a little different. We're tied off the chicken eyes right now. And it's illegal.
So you see what they're doing here? They're able to cut and trim the blank easily and the whole core because this is here pre-tension. So in pre-tension, there's no problem to trim any part of it. In post-tension, you cannot do this. It's gonna be a disaster. And someone can just get killed easily in a case like this in post-tension. So in pre-tension, there's no problem as long as you know what you're doing. Keep this please in mind.
Professor, could you please explain what are those holes again on the concrete?
This system here, this is hollow
Yes.
blanks, hollow core blanks.
Yes.
This is like instead of having reinforced concrete slab, you know when you have reinforced concrete slab?
Right.
I'm sure that you have studied this. I may take you back here to this. You have a wall here. You have wall on the four sides of this building. And this can be used as parking structure.
Right.
So you cannot allow any columns in the middle, and of course you cannot have like posts and stuff like this, like wood, right? So
Right.
like you have to have a big span, right?
I
So the way to
see.
do it, yeah, and this is the pavement. Let's look at the picture from the beginning. You see that you have concrete walls. See this?
Right.
You see? This wall is below grade. So this is usually it's gonna be used as a pavement wall, like a retaining wall. And then you come on the top, you put all of these blanks, the hollow core. So you have a support here. This is gonna be one support. This is gonna be one support here. And then this blank here spans from here to there. So this is gonna be the design, right? It's gonna be for this length. And of course, it's gonna be full of this cables. They have cables at the bottom, right? They put it in place, and then after that, they pour some concrete on the top of it. to level it. Because like this, you cannot put a carpet here or floor, correct? This is not a good like topping and flat topping, you know, it needs to be flat and level. So after they're done, they're gonna put some concrete topping, and this concrete topping for seismic it works as your diaphragm. If you're familiar with the diaphragm design, or if you heard about it, and then after that you just use it. So you have a system that you're able to assemble in one day. Just imagine if you like to put here a concrete slab, how much time you need to put the reinforcing and the formwork, right? And then you put the concrete, and then you wait like a week before you take the form out, before you strip it out, right? So this is actually an excellent solution for a case like
How are
that.
they anchoring those?
They're not going to anchor it, just put it in place, and then the concrete topping is going to have some reinforcing. So they put the reinforcing in the concrete topping, and this is what we do in precast, pre-stressed parking structures. I'm going to show you lots of details about this. It's going to be coming. I'm going to show you the detail of it, what the reinforcement is going to happen, and this kind of stuff. Now, in a case like this is just heavy. It's going to stay in place. And once you put the concrete topping, it's going to set it in place. And of course, once the concrete is going to start to harden, you know. In California, it's different. In California, you need like very good detailed connections for the seismic. The Midwest is not really critical in lots of other states, you know. But it gives you an idea that this can be a perfect solution even for some housing here, for housing projects. And look at this. This is like the basement. This one you go down to the parking structure, to the garage. And then after that, they start to put the concrete on the top. Look at the concrete. Just put some concrete topping. It works beautiful with no reinforcing. Because actually in this state, they don't really need any reinforcing. There is no seismic. This makes sense to you?
Professor, are all these pieces like manufactured off-site and then just bring them in, or
What do you mean?
like
This piece is like all
like
of
the
this piece,
hollow,
right?
the hollow
The hollow
core?
core itself
Yeah.
is done in the factory.
And they just bring it in and place it in.
Yes, yes. I'm gonna show you more videos on this, how it is done in the factory.
What's the reason for the trimming? Is it just to make it fit better?
Yeah, to make it fit, exactly.
Oh, okay.
Yeah, because this is a beautiful thing about the pre-tension. For the pre-tension, you can just trim it, you can cut it, you can do notch, you can do anything you want it. Because you have full bond between the cable or the tendon and between the concrete. In post-tension, you cannot do this. I don't know if you guys have heard about post-tension. Some people are trying to, let's say, to work on post-tension slab or post-tension slab on grade or elevated, and someone was killed or something. I don't know if you guys hear about this. But usually we tell the people, contractors, please don't just play with the post-tension, especially. And some people, they don't care. They bring a saw and just saw cut it, you know, they don't care. You don't feel the problem.
So, Professor, how we know this one is post-tension?
What's that?
How do we know this one is post-tension?
In post-tension, you wouldn't believe it. There's a stamp that they put on the top of the concrete. Do you know anyone, let's say that you visit a house, let's say in the area of Irvine, or area maybe Mission View. Once you go there, or Compton, Torrance, lots of houses, new construction, they're made out of the concrete slab on grade. They do it out of PT slab, and they get this stamp in the garage. Because the garage use is not going to be covered, right? Usually the rest of the house is going to be covered either with some flooring or tiles or carpet or whatever.
Yes.
But for the garage use, it's going to stay as is. So they come right next to the entrance of the garage, like the gate, the garage door, and then they're going to see a stamp. It says PT slab. Just keep an eye on stuff like this.
Okay.
And the big problem is going to happen when plumbers wants to work there and they like to fix something, right? And they have to cut the slab. They don't care. They just cut it. They can drill through it. They don't care. and from time to time you hear about a disaster in one of these cases. You know?
So, Professor, for the houses here in like in Orange County and here LA, it's most of them. It's like it will be not concrete, right? Only the garage or something, but the building is not concrete.
The PT slab that I'm telling you about, this is in any house, especially in Irvine. And the reason that we use it because there is a soil called expansive soil. I don't know if you hear about expansive soil before.
Yeah.
Okay.
Yeah.
Expansive soil is this type of clay that once is gonna sense the moisture. Once you add water to it, it's gonna enlarge in size.
Yeah.
It's gonna push whatever above it. It can just bring the entire house up.
Oh yeah.
Yeah. So this expansive soil, usually there is certain precautions to it. For example, we usually when we do a design for an area with expansive soil, we do like cut-off wall. So in the perimeter, we do with little bit deep foundation. We go like 5-6 feet on the perimeter, sometimes 3 feet, depends on the expensivity of it, on the properties. And also in many cases, we try to add lots of moisture before construction. Right before you pour the concrete slab, you add lots of moisture. So it's gonna go all the way up, right? It's gonna expand. It's gonna take the maximum size it can go to. And then we pour the concrete right at this point. And then when we pour the concrete, of course, the concrete most likely is gonna be PT slab. So when the soil is gonna shrink back again, and you walk in the slab itself is gonna be able to take the pressure, the loads from the top. And also, if you have some pressure come from the soil, the slab also is gonna be able to take this pressure that's come from the bottom. This is the reason that we like to use there like PT slabs. It's gonna be much stronger.
Okay, thank you.
Again, the problem is gonna be in some contractors if they are not aware of it. And I'm talking about like wood construction, like houses, regular houses, and you see it there next to the garage door, and sometimes the owner doesn't know. They don't know that it is really dangerous to touch stuff like this. And again, from time to time, we see some disasters, and we hear about it, you know. But what can you do? People sometimes don't care, and they're not aware
So
of it.
Professor, in post tension, they put the cables through after they pour it.
No, they put the cable before.
Okay, how come they call it post tension?
Okay, they put the cable through a conduit, you know, like electric conduit, like a pipe,
Yeah,
hollow pipe. But it's not that big. I mean, it's not like 2 inches. It's almost slightly larger than the rebar size or the cable size. And then they put in the concrete, and then they pour the concrete around it. Now the concrete is gonna be out of the conduit, right? There is no direct contact between the concrete and the tendon or the cable. And then once you start to apply, now the cable is kind of loose because after you pour the concrete, let's say 2-3 days after this, if you like to pull it a little bit, you can. If a couple of guys wants to pull it from one side to the other side, you should be able to. But it's gonna be kind of a little bit hard. And usually there is grease, I mean, between the cable and between the conduit or the sleeve, they call it the sleeve, they have this grease. They have certain amount of grease that they put there to protect it from rusting. And after you do this, you go from one side, you put the anchor. Anchor is gonna be like a connection that you put at one end. And then you have a jack, you come from the other side, now you start to pull it, the cable. So you see what happens? It is gonna be post tension. It's gonna be after you pour the concrete. Now there is no good bond between, or sometimes there is no bond at all between the cable and between the concrete. Now the problem is, if you're gonna come in the middle, just imagine now you have a cable inside the sleeve, and you have some grease, and then you have 2 anchors from each side, right? And then you come in the middle, and then you cut the cable. What's gonna happen to one of these blocks, like the anchorage at the end? What do you expect? It's gonna fly out, and it can kill anyone easily. Easily. I mean, it's gonna kill maybe 2 people. I mean, if it hits a couple of people, it's gonna just kill them. This is a problem. So it depends on the type of the slab that you have there. And also, once you cut the cable, you're gonna be losing the pre-stressing, and you cannot put it back. I mean, how would you retrofit this? Just imagine that you have a concrete slab. There's a cable, you cut it. How would you put it back? You cannot. We're not talking about 2-3 feet. We're talking about maybe 30 feet or 40 feet of cable, right? So you cannot really take it out. It could be a disaster, as they say. As I said, the good thing about this pre-tension that you can just trim it easily. Look at what happened here. Look at this concrete saw, and you can just make it a little bit shorter. And look at the cables. The cables are extended from one side. Show what's happening here.
Professor, do the cables always go one way, or do they ever go like?
No,
two
usually it's gonna be
ways?
in one way, not two ways. It's gonna be one way. You see here the cables. You see this? They're gonna be in the bottom. This is gonna be the bottom. You cannot put it upside down. If you put upside down, it's gonna collapse, right? Because all the tension members, all the rebars is gonna be at the bottom. And if you see here, there's no ties. Didn't you notice this? No ties, no stirrups. It's gonna be just like that, and performs amazing. I mean, I know a friend. He has some connection with a precaster because this is not easy to find. You know, I mean, unless you have a really big house. And he has a small house. He wants to do a small basement, and he's an engineer. I mean, this is how he was able to connect with one of the precasters, and they give him, I guess, like 5 or 6 blanks as a gift. It was not worth it, but he paid for transportation. And he did his garage. That was very nice. I looked at it. I said, "Wow, this is very good." So use precast blanks.
What did he do for the walls?
Yeah, he did the walls, like masonry walls. He did, of course, the design, the analysis, the calculation. It was 2-car garage that he wants to do it as in the pavement. He was in West LA, and it looks very good.
So, Professor, they're always on the bottom, right? Like,
yes.
You know, like in the previous design course where we would put like repars on the top where the
yes. For compression,
like at the columns, yeah, where the tension switch sides.
Yeah.
You don't need to do that for this.
Okay. For this precast members like blanks and double T's, you don't go continuous. It's gonna be all simply supported. In bridges, you go continuous. In elevated slabs, like the project I told you about in San Francisco, that was continuous slab. It was post tension. So we were able to go top and bottom. Whenever I need it in tension, I'm gonna put it there. And also I can add a little bit of reinforcing. But usually it's gonna be like simply supported, stuff like this. I mean, you don't really need any rebars on the top because you don't need that. It's not needed. It's gonna be much cheaper when you just do it this way.
Mm-hmm.
So you don't want to add complexity to it. You don't want to add top steel and then hold it in place and put some chairs. You know, this is gonna be expensive in this case. You'd like to go as simple as possible because this is gonna be like mass production. So you cannot afford to put compression reinforcing. You just add more tension at the bottom. That's what you do.
And are those cables, do they come in like different gauges?
Yeah, they have size. It is very similar system to what you do in rebars, right? You have different size. Yeah, comes in different size. Let's finish this. Then there's another one very famous for his pancreas. This is a good virtual tour. At least you know what's happening there. You know. You don't need that. But look what happened here. This is like in the yard after they cast it. Look what happened. This is inside, and of course this is gonna be like the open yard. This is where they store the product after they're done. You see how it's stored. Here's a double T. They do it in layers. So this is like the storage yard. And look at this. This is gonna be the crane. They're gonna be carrying with this guy, and this guy just moves. You can just ride it. You know, you can drive it. Here's the cabin, and you can just move it because this is gonna be carrying the entire. Like it can carry up to 3 or 4. You know. Here's the concrete after the cast. Here's the bed, the casting bed inside. You see the casting bed, and then they stop here, and then another one they stop here. Actually, this is like the abutment. You remember the abutment that I showed the picture of, which is this one here. But they have continuity. They have the cable. So actually, the cable, when they do the tension, the cable goes from here all the way to the end. One cable. Of course, it's not going to be just one. You're going to have a few of them, but it's going to be like one piece. And this is going to be like one of the abutments, right? You have one abutment here, you have one abutment at the end. This is going to be like dividers. And then they put the reinforcing, they put the cables, they do the tension because it's going to be pre-tension. And now after that, they put the concrete, they finish it. Just music. You see the double T? Wow. See how long? The length of it. And here's the concrete after they cast it. And you see also the hollow core. Okay, there's another good one.
Do these pieces, are they like modular or do they have to be like pre-designed?
No, it is all modular and also pre-designed. Look at what happened here. See this?
In this case, a double T. A double T is used primarily in parking structures, but can be used in virtually any type of building, including office buildings, industrial buildings, and schools, to name a few.
Double Ts are kind of a unique product with having a capability of having a very long span. When we start talking long spans, you're talking 60 feet plus, and sometimes goes as high as 120 feet.
The typical day of a pre-stressing plant usually starts very early in the morning. The product from the previous day's casting has cured by now, and the pieces need to be stripped from the form to get ready for today's casting. For any pre-stressing plant, it is very important to maintain a clean plant. Maintaining neatness is not only positive, video will explain but also safety standpoint, since any debris that might be left over from the day before.
Yes, this is not a good quality one. I have a better quality. I have the actual file.
Stressed concrete unit at a pre-stressing plant. In this case, a double T.
Here's a double T.
Is 120 feet.
May be fixed forms with an appropriate draft to allow for easy stripping. Once the bed is cleaned, it's ready for setting up today's cast. This particular bed is set up for 5 double Ts, each about 60 feet long. The bed has a total length of 400 feet. This is a self-stressing form, where the form itself is designed to take the total pre-stress force in compression and also to handle the eccentricity of the strands. Sometimes the producer may use a form that is set between bulkheads that are built right into the ground. The pre-stressing force is then resisted entirely by the bulkheads and their foundations. Next, the strands are placed in the form and extended from end to end. Crew members thread the strands through each of the dividers and then run them through the stressing plates at each end. The typical spacing of the strands is approximately 2 inches. This divider is a steel device that separates the individual double T units from one another. A gap of about a
place. So what he's talking about, this thing that he put in there is just to keep it in place.
Is approximately 2 inches.
2 inches for the space between these two cables.
This divider is a steel device that separates the individual double T units from one another. A gap of about a foot is typical between the ends of the adjacent pieces. This gap is required so the strands can be accessed and cut, and that each double T can be stripped. A gap of about a foot is typical between the ends of the adjacent pieces. This gap
and cut it, which means the strand is going to be continuous, right? And then they're going to come here and just trim it. They're going to do this after the concrete is hardened. They're going to do this with a small grinder.
Gap is required so the strands can be accessed and cut, and that each double T can be stripped from the forms. The next step is the tensioning of the strands. In this case, we have a strand pattern with straight strands of 6 strands in each stem.
This is the anchor that I was talking about. There's going to put an anchor here to each one of these cables. And the anchor, you just put it in here, and then from the other side, once you start to apply any tension to it, it's going to get locked.
As shown here. The strands are first tensioned to about 2 to 5 kips based on the gauge pressure reading. In this case, a mark is made on the strand after the preload is applied.
Now the question is, how would you measure the tension on the strand? What is the easiest way? Now there's 2 ways of doing it. You have the properties of the strand itself, which means that you know the stress-strain relationship. So you know, let's say if you have 400-foot long piece for a strand, if you like to apply tension of this much, you need to apply a strain of this much. So how much is the strain? Let's say if you're going to be taking this 400 feet and you're going to have an extension of 1 inch. So what does it mean by that? You figure out the strain. You say the strain is going to be equal to 1 inch divided by 400 feet divided by 12, because the strain is going to be unitless. After that, you take this strain and then you go to the stress-strain curve and then figure out the amount of stress that you put in the cable. There's another way also that you can have a load cell. With the load cell, you can read the force directly, or it's going to be based on the pressure that you put in the machine in the jack itself.
The strand is then tensioned to the specified level and is measured using the gauge pressure on the hydraulic pump. The QC technician then checks the elongation against the theoretical elongation. The requirement that is the force on the gauge and the elongation must match within 5%. If that tolerance is not achieved, the reason must be established and the strand may have to be detensioned and retensioned. After the strands of this double T are...
Now you see also you have this mesh that you put on the top. It's going to be very light mesh. Of course, it's going to be a mesh, welded mesh. So it comes like pre-welded. Otherwise, it's going to be taking forever to lay the rebars and time to each other.
All stressed, the remaining embeds are set in place. These include stem reinforcing, lifting devices that will be used to strip and handle the piece, forms for blockouts in the flange, and forms for blockouts in the stems, flange reinforcing,
and
flange connectors or vectors along the edges. In this case, one of the double T's in the bed has typical flange connectors applied along one edge and special flat plate connectors applied along the other edge to accommodate connections across an expansion joint. The form is now ready to have...
This is the connection I told you about, that this is to connect between another one and between the beam or another edge.
Concrete poured, but only after a pre-pour quality control check has been made and the QC person signs off on it. This QC check can also be done by the bed superintendent and depends on the particular plant's practices. Either way, the check is critical to ensure an end product with the highest quality.
There's all these things you look for. The mesh, you look for anything that could be touching the stems on the bottom, like any wire ties that might have fell in there, because that would develop some type of a rust spot. You check the length. You want to make sure that the damps are correct. Do we have the strand stripped properly? So there are a lot of critical areas that you need to verify.
Concrete is mixed at the batch plant under tightly controlled conditions. The cement is supplied using tanker trucks. Here, the cement is being blown from the tanker through piping to the cement silos. When needed, aggregates are delivered to bins in the batch plant. The aggregates are stored outside of the batch plant in separate bins. In this case, an enclosed vertical bin system is utilized. During winter, in northern climates, the aggregates must be heated to get them to flow properly through the batching system and to maintain proper concrete mix temperatures. Payloaders are used to shuffle the materials to the conveyor belt. Computers are used to proportion the materials for the desired concrete mix. Cement, sand, stone, water, and admixtures are measured according to signals from the computer. After the concrete is mixed, it is discharged into a delivery device. It's imperative that the concrete mix be delivered to the form as soon as possible. These vehicles are called tuckers, and they are used to deliver the concrete to the bed in the yard.
Just, the concrete mix that they are working with is going to harden faster than any other concrete. So this is unlike the conventional concrete, that use the encased in place.
A self-consolidating concrete is being used to cast these particular double T's. With this type of concrete, vibration is not required to consolidate the concrete. However, minor controlled vibration is used in the double T stems to help remove air from the sides of the form, reducing bug holes in the stems. There are many advantages in using this type of concrete.
We do use self-consolidating concrete for our double T's. We feel that it gives us a better finish. We feel that it's easier to place, takes less labor, less strain on the labor to place that concrete.
The QC department will make the necessary tests at this time, including a temperature check of the concrete. Since SCC is being used here, a spread test is done to check the concrete flow in lieu of a slump test. The spread is measured to assure conformance to the planned spread.
You see, in conventional concrete, it doesn't do this, right? It's going to drop only maybe 2 to 3 inches, maybe 4 inches, not more than this.
The edges of the circle of concrete are the potential for plastic shrinkage cracking. The final finish will vary depending on the use of the double T. If a cast-in-place topping is necessary, the surface will be made very rough so that a good bond will be achieved. If it is a roof, the finish will be relatively smooth, but not necessarily perfect. In this case, the surface is...
So the reason that we do the broom thing to provide the roughness so that the new topping, when it comes on top of it, is going to be bond to it. So just amazing when you think about this concrete topping that we put in all parking structures here, there is no actual dowels or nothing like mechanical connection between the concrete topping and between the top of the double T. It's going to be just based on this friction thing.
Groomed as these double T's are being used in a parking structure. Different patterns can be applied depending on the needs of the project. The bed is now in its curing stage. Sometimes, particularly in cold climates, the double T may be covered with tarps. In other areas, they may be open. Accelerated curing is often done using live steam or radiant heat from heaters attached to the form itself.
Double T's for parking garages really need to be held to a high standard. When they're assembled in a garage, they make the finished surface. There are tolerances for putting these pieces together, offsets in the surfaces. All of the connections are very sensitive as well. To be executed properly, the embedments in the double T have to be placed properly. So there, again, are a lot of critical issues that you have to be concerned with to get proper performance out of that simple double T.
After 12 to 16 hours of curing, the T's are ready to be stripped. The QC department first tests the concrete to be sure it has achieved the strength required to detension the strands, typically 3,500 psi. This is a typical test being conducted. The strands are detensioned in a specific sequence established by the QC department or the plant engineer.
At the bottom,
here, personnel are positioned at each end of the bed and at some of the intermediate bulkhead locations. On a signal, they burn the strand at each end. After all the strands are cut and block-out formwork has been removed, the T's are stripped from the form. Cables are attached to the lifting devices, and each piece is removed and transported to a detailing area for any minor cosmetic touch-ups. Also at this time, the QC department does a post-pour QC check on each piece that is brought to the detailing area.
When I first get back there, I go and check the length of the piece and verify that within, there's a tolerance of probably 1/4 inch or so. Check the width, we check the vectors, we check the electrical blockouts. I do a visual for any type of discoloration in the stems underneath the piece, any type of surface cracks, bug holes, just do a complete visual.
Any defects are noted so that repairs can be done before shipping the tee. After all the work is completed, the double tees are moved into the storage area where they are typically stacked using appropriate dunnage located near the ends. When the job site requires the tee to be shipped, it is loaded on a trailer and transported to the job site. What you have just observed is the process for making one type of pre-stressed product. These other types are made using essentially the same process. Hollow core plank, which are used for floor and roof components in multifamily housing, schools, hotels, and many other buildings. Inverted T-beams, which can be used in any total precast concrete build system. Columns, which are cast horizontally and then rotated in the air at the job site. They are often designed as pre-stressed components. Architectural spandrels used in office buildings and parking structures can be made using the pre-stressing process. Deck slabs and box beams, which are used primarily in short span bridge construction. Standard ash-toe girders, which are used in long span bridge construction. Standard bulb tees are also used in long span bridge construction. Pre-stressed piles that support any type of building in areas that have unfavorable soil conditions. As you can see, there are many types of pre-stressed products available. The variety of products that can be pre-stressed in a long line operation is almost unlimited and is up to the imagination of the design professional.
We really do encourage our customers and architects and engineers to get to our plants to really understand how precast concrete is made. They need an understanding of the high quality that they can get out of precast concrete as opposed to the random quality that you might get out of cast-in-place concrete.
Well, it's important that we do things as efficiently as we can and as cost effectively as we can, but also as well as we can. And it's not only my responsibility, but the responsibility of everybody here, management, labor, everybody included, to do the best job that they can to, at the end of the day, make a little bit of money, but also have a customer that's very happy and will possibly want to have some return work coming back our way.
Did you guys notice this? That when they carry this, they put two supports, one at each end, right? They don't try to put it completely flush on the flatbed. Did you guys notice this? Talk about this.
Is like vibration from the truck?
Say it again, please.
Is that are those there to prevent vibrations from the truck from messing it up?
Yeah, this is one of the reasons, but look at this 2 slides before we finish for today. So here's the bed. This is just a schematic. It's not the actual, because you have seen the actual, and actual is going to be taking more than one. You have here dividers, and you're going to be putting more than one piece at the same time. And then after that, you're going to be burning it, or you're going to be cutting it. It depends on the size of it. Look what happened, the process for the pre-tension. You have the cable between the 2 abutments. You put the concrete, and then after you cut it. So what's going to happen? Once you transfer the force, once you cut this and cut this, you're going to be transferring the force here to the beam. So what does it mean? It means axial load. Now, is this happen? Is this concentric or eccentric? Yeah, say here's the center line, right? It's the centroid line. Is this eccentric or concentric?
Eccentric.
Eccentric. So it means that as if you're going to have here a point load and a moment. Now you have combined loading. This is why I said combined loading is going to be very important. We need to study the stress, and you're going to see that this is really important, right? It is not really the number of cables that we put in there. It just depends on the design. So there's no set number of cables that you put at the bottom of the double T. In many cases, you just have 2 on each side. So this is the reason that without even you start to use this piece or the structure member, it's going to be exposed to lots of stresses. Because once you cut the cable from this both sides, you're going to have lots of compression on this member. And the compression is going to be at the bottom. This is why you don't want to really sit in a flat area here or flat bed. You'd like to have it here in 2 supports. Because when you have it in 2 supports, guess what's going to happen? The self-weight of the structure member itself is going to be pushing it down. And this structure member is going to be almost flat. Does it make sense? Yes or no?
Yeah.
Okay.
Yes.
All right. We will continue next time, and you're going to see sometimes you have discontinuity, When you have continuous, you're going to be taking the cable or the tendon, you're going to be taken up and down. But when you have simply supported in a planet, like for this pre-tension, most likely it's going to be straight. You don't want to make it complicated, otherwise it's not going to be cost effective. Don't forget here that you're looking for mass production. That's why you don't just put one piece. You're going to put more than one piece and then cut it, like the video, right? If you like to be more efficient in putting this cable, you're going to put it like in a drape shape like this. You're going to drape it. So it's going to be like exactly the same as the deformed shape of the beam. Just imagine if you have a conventional beam, like a homogeneous beam, and then you start to load it. This is going to be the deformed shape. So usually we try to make this cable here to follow the same as the deformed shape of the beam. If I have continuous, guess what's going to happen? Deformed shape of the beam is going to look like this. And the best way is just to make this cable here to follow the deformed shape of the beam. It's going to be the most efficient way of doing it. So this way, it is not very efficient for the structural use of it, but it's going to be very efficient money-wise. So when it comes to the cost, this is going to be like the cheapest way of doing it. That's why they have this in factories and precast yards. Any questions? Yes?
Professor, do we have homework next week?
Do you have what? A homework? Yeah.
Yes.
Yeah, it's going to be a simple homework because you don't have here lots of answers.
Okay, because I didn't see the homework on the Canvas, so.
Yes. I'll post it there. Don't forget, the homework is going to be due not over the weekend. It's going to be due right before next lecture.
Yeah, thank you.
All right, go ahead and sign out. You guys have a good night.